In our lecture 6 directory, and I'm going to fire up the Miralles model in VENSIM for the case of the Miralles, and let's see how it shows up. Max out the window as I did before. Alright, so here is the model we were just discussing about the Maya demise, the Maya collapse in VENSIM. Okay, we have population of Mayas, and I'm gonna look at the equations and go with it. I'm gonna click there, and we're gonna see here the Mayas are the units are, so it's a level variable, so it's in stock. It's units are given in people, person. It's the difference between the natural increase. And in this case, just let me remind you that this natural increase includes, this is births minus deaths, so this is the net increase minus the emigration, and the initial value is about 100,000. And here, so a little note, if we assume 2 million inhabitants at the moment of collapse at about year 1000 AD, we can obtain an initial value in the year 1000 BC with a rate of 0.17 annual per growth percent, which has been estimated given the given some records that indicated that the population was doubling in about 400 years. So this is this gives that 0.17. So if you backtrack that to year 1000 BC, this gives you about 1,000 people to start with. Okay, so that's about the initial condition. Time is 1,000 years BC, 100,000 people. Okay, and this will, with this growth rate, this will take us to about 2 million people at essentially 2,000 years later, 1000 AD. All right, so that's the population stock. So the natural increase is driven by as you will see, it's driven by population and the natural increase rate. Okay, and this is people per year, and the natural increase rate is essentially this 0.17%. If you go here to the equation, if you click on natural increase rate, you'll get essentially the 0.17%. Okay. And this is a little bit of the dialogue. Okay, so population grew because of that, and the migration of people had to do with the availability of food. Okay, so essentially, we're assuming that if we know the gap in food that existed in kilograms per year and the consumption per person, we can obtain the equivalent number of people that will be without food. Okay, and essentially we'll assume that a fraction of that, which we'll call the emigration ratio, will leave. So there'll be a fraction of people that don't have enough food that will choose to leave, and that was that's to have something in there in the persons per year, and the immigration ratio that was given there was 5%. Okay, so 5% of people per year would migrate, of those that have lack of food. Okay, so let's take a look at the consumed food per person, and here we essentially assume that there is a given value, okay, of 400 kilograms per person per year. Okay, so, and this is essentially assuming that there's a little bit more than a kilo a person per day. Roughly, that's what you would eat. Okay, so this drives the population, the amount of people, and the consumed food per person will essentially determine the demand for food. Okay, and let's see what that looks like. It's the product of the population and the consumed food per person will give you the kilograms per year of food demand overall for that population. Fairly straightforward. Now let's take a look at how food is produced. So I'm going to start essentially from the top, and then we'll drive towards that food produced. So food produced will tell us the gap, and the gap will tell us essentially how the population can grow with the availability of food. So it all starts with the forest, okay? And you'll see what the little bit of the discussion that we had. Um, Forest is stock variable. It's given in square kilometers, so it's an aerial variable, and forest gets essentially deforested. There's no creation of forest. Forest can just be deforested, so it's a negative. There's only an out, and you see in the schematic that there's no forest being created, and that's probably okay an assumption. And the initial value of 5,000 square kilometers was essentially estimated from an assumed population density of 400 people per square kilometer, which at the time of the demise, if you take the 200,000 people, divide by the area in which they were at, it'll give you about that density. So if you divide the 2 million people by about 400 density 400 square kilometers, that will give you about 5,000 square kilometers of forests that were available at the time, or at least originally. So let's get out of this. So the forests get deforested and get transformed to lands. So I'm gonna go to lands first, and then I'll come back to the deforestation. And lands is a stock that it only gets produced. So when we talk about land, is essentially cultivated land. Cultivated land is found through deforestation. Okay, so it's produced by deforestation, and it's got an initial value of 8 square kilometers, and this initial value is obtained from the total food consumed, and this is the if you look at the 100,000 people initially. Times the 400 kilos, then you get 40 million kilograms each year, and the initial fertility of the land, which we'll see in a second, it was 5 million. This is an assumed value of 5 million kilograms per square kilometer per year. So if you divide the two, you get an 8 for the square kilometers of initial. So the 8 square kilometers supported the 100,000 people that were there in 1000 AD. Okay. So if we look at now deforestation, this is the conversion of land from forest to cultivated land, and this is it's given. First of all, it's given in square kilometers per year. Okay, and let me go to the comment before we look at the equation. And so it's a little bit. There's a little bit of an explanation here. The idea is that the Mayas deforest the amount of square kilometers that they need to close the gap in food. Okay, considering the fertility of the land. The max function that appears in the equation is used to prevent error if the model needs to divide by 0, which is a common VENSIM trick to avoid blow-ups. The min function is used to provide a bound for the annual deforestation, and I'll tell you about it in a second. The time step gives us a way to convert the deforestation to a rate. This means that every year they deforest all the forest they need that year. So what this model assumes is something. It's that the Mayas were sort of rational. They would get an idea of how much. They will look at the gap of food they had, and they will only deforest whatever they had to deforest. So they had some environmental conscience, but that conscience was counteracted by the need of food. Okay, so then the equation then becomes, and this is what this is. This translates into VENSIM as follows. Let me look at the max first. First, they would look at the fertility of the lands, and this ratio of 1, and actually let me explain what this this is essentially the fertility of the lands will be essentially the amount of land that is the amount of land that's still fertile. Okay, the land gets reused, and it's not fertile every time. And there's another variable in the model that explains that the lands lose fertility. Okay, now if you divide the gap of food by the land, then this gives you an idea of how much food per unit square kilometer it's needed. Okay, now we throw the max in here because just to avoid a situation in which we would be dividing by zero. Say that you completely run out of fertile lands, then this will give you an error. So that's why this is here. So if you compare the ratio of the gap of food divided by the available fertile land, which is the ability of food being produced per unit area or per unit land, and you compare that with essentially and I'll define this variable in a second, the maximum annual deforestation times the forest available. If you compare those two, what you're saying is that the Mayas deforested the minimum they needed to produce the food that they required. Okay, and then you divide that by the time step, which in this case is a year, to convert that to a rate of deforestation. Okay, so let me go back and look at this variable, the maximum annual deforestation, and this essentially assumes that even the Mayas had some environmental conscience. So this is a limit imposed to account for some rationale of environmental impacts that the Mayas had. So in any case, the Mayas would say that no more than 4% of available forest will be deforested. So that's why they would say the minimum. Okay, so if you go back to deforestation again, so they chose. Okay, they chose the least of their gaps and that maximum deforestation rate. So if they needed more food than the 4% of available forest would provide, okay, which is this product here, they would choose the 4%. Okay, if they needed less than the 4%, then they will close the gap. So this meant that the Mayas, in this case, that the Mayas had some ability to adjust for food consumption in the case and not deforest too much. So there was some environmental conscience to them. Okay. So this runs us to the concept of land, fertility of lands, and this is used. This talk is used to account for the fact that the lands, as they become used, they become less fertile because your nutrients in soil get consumed, and it's a natural process. So in this case, the fertility of the lands, which is a stock, and it's got units of kilograms of food produced per square kilometer of land that is cultivated per year. Okay, and it has an initial value of 5 million, which means that this is 5 million kilograms per square kilometer per year. Then you can get the food you can sustain for the 100,000 people that were there in the beginning, being fed each at 400 kilograms per year. Okay, so that's the initial fertility, but the initial fertility gets attenuated by the losses. And the losses here are, let me read the text here. The losses of fertility are proportional to the fertility that exists. So there's a fertility that's there to begin with, and then a ratio of the lands to the forests with an exponent. Okay, and here I just wanted to introduce like a little equation. We could have done this with the table as well. And I encourage you to experiment with that if you wish. But essentially here, essentially what this says is that the loss of fertility, it's it's a product of the available fertility, so the fertility of lands times the minimum of either 1, okay, which means 1 means essentially there's no loss of fertility, okay, or a ratio of lands to forests squared, okay, and this means essentially that if if for example, if the amount of land you're cultivated compared to your forest availability is larger than 1, you can and you square that, and this is just a sort of an empirical relationship. But if that happens and this goes beyond 1, then you're going to be losing essentially losing fertility. Okay. And it's curious that if you use an exponent of 1.9, you see the collapse in year 800. I use an exponent of 2 in this model, and then you can see the collapse in year 1000. So that's essentially how that relationship works. So this is just an expression to go from the fertility of the lands to the losses. Okay, so that's essentially it. So let's see how these translate into the food produced, which closes the gap. And the food produced is really just the availability of lands times their fertility. Okay, so it's a product. It's got kilograms per year as units, and this will tell you the amount of food that's produced. So that's essentially how the model does. If you want to put it in a nutshell, essentially, population grows limited by a demand for food. Okay, the demand for food it's driven by the population, and it's compared to a gap. The gap is created with the food that's produced, which is driven by the conversion of forest to lands and the fertility of these lands. Okay, and how how that gets affects deforestation. So forests get deforested to produce lands. Lands provide fertility that is lost over time, and that generates the lands times the fertility of lands generates food. That food gets compared to the demand of food in this gap, which then drives migration, population, and that's how the feedback works. And you can, with the model setup, you can just run it and generate the graphs. So you can look at the population, and these are the graphs that we saw in the lecture. And you can look at the population graph. And I think I have one of these graphs that that was pre-produced. Let me see if I click here. Here we go, graphs. And there's a graph here that I created, and you can display it. And this is the graph that I show, and you can actually edit it and go in there and show it. But that's essentially the one that shows population in blue, which has the growth, the exponential growth, and then the collapse in year 1000. The fertility of the lands, which is in red here, and you can see how it collapsed, as well as the forest, how it collapsed. So this is a nice model to explain how the Mayas essentially drove themselves by too much deforestation, even though they had their checks, which is interesting. They had their checks on deforestation, but even though the population, the fertility of the lands was never able to catch up with the availability of forests, and the fertility of lands were never able to catch up with the exponential growth. Okay, so it's kind of an interesting story, and it also shows how things can collapse very quickly to a point that it's not able to recover. Okay, which is also interesting. So I'll leave the discussion here of the Maya case. I encourage you to play with this model, change parameters, and look at how you would vary things to look at different outcomes. Okay. Another thought that I want to throw at you, although I don't expect you to fully engage in it now, but how would you include droughts in this model? Okay, it's sort of implicit here because we have the losses of fertility, but think about how you incorporate drought into this. And it's a nice thought exercise. Okay, so I'm going to leave it at that, and we'll move on to the next case study.